Look at the surface of this iron chain. Over time, the hard, pristine metal degrades into a rough, brittle orange powder. Take a thin strip of magnesium ribbon, add a spark, and it ignites into a brilliant white flare. Even a fresh apple left on a counter breaks down, browning and collapsing as the organic tissue spoils. These materials are undergoing a total transformation. Their atoms are physically separating and reforming into alternating pairs with entirely different properties. Individual atoms are far too small to see, meaning we cannot directly witness this microscopic reshuffling with our own eyes. To prove an invisible atomic transformation occurred, we have to look for specific physical indicators left behind in the macroscopic world. When atoms swap partners, the new structures they build leave behind distinct observable signatures. These signatures manifest as a shift in physical color, like rust on iron, or detectable odors, like spoiled fruit. A reaction can also cause a sudden change in state, or a transfer of heat as energy is absorbed or released. These 5 indicators form a checklist known as FECs: formation of a precipitate, evolution of a gas, color change, temperature shift, and state change. While checking off these boxes proves a reaction happened, it doesn't reveal the exact ratio of the atoms involved. To track the precise movements of every single atom, scientists require a strict mathematical shorthand. That shorthand is the chemical equation. It translates messy, real-world events into precise, trackable mathematics. Every equation follows the same structure. The initial ingredients, the reactants, sit on the left. An arrow indicates the transformation. The newly built substances, the products, sit on the right. This entire system is governed by a single principle: the law of conservation of mass. Atoms cannot be created or destroyed. The exact number of atoms at the start must be present at the end. If they don't match, we add coefficients, multipliers placed before molecules to equalize the atomic count on both sides. A mathematically balanced equation is the only way to verify that we understand the exact atomic accounting of a real-world event. Of the millions of possible chemical combinations, atoms trade partners following just 5 predictable architectural patterns. In a combination reaction, 2 simple reactants merge to form a single, more complex product. A decomposition reaction runs in reverse, splitting a single compound apart into simpler pieces. During a displacement reaction, a highly reactive element forces a weaker element out of its partnership. In a double displacement, 2 different compounds mutually exchange their ions to generate 2 new products. Finally, there are redox reactions. This involves a specialized transfer where one substance gains oxygen, oxidation, and the other loses it, reduction. These 5 structural blueprints describe every instance of chemical transformation in the universe. We can see the physical weight of these blueprints by looking at the impact of just one process: oxidation. The slow addition of oxygen to metals creates corrosion. It pulls iron atoms out of a solid steel beam, flaking away its structural integrity until it fails. That same oxidation process attacks the fats and oils in our food. This leads to rancidity, causing organic material to turn toxic. When oxidation happens rapidly, it releases energy as combustion, giving us the fire used to cook meals or the thrust that drives vehicle engines. Balancing these equations allows us to calculate exactly how matter will behave before the first spark is even struck.